We are live.
Okay, so please record the session also, YouTube. Okay, thank you. Uh, Good morning, everyone. This is Dr. Kollabanu Prakash, IEEE Senior Member, working as Professor in Computer Science Engineering Department from KL University, Andhra Pradesh, India. So, to just briefly give about myself, I published nearly 80 Scopus Index publications till date, and overall more than 100 publications indexed in Google Scholar with a H index of 17. And I am an editor for around 12 books, internationally reputed publishers like IEEE, Wiley, Springer, Digruter, CRC Academic Press. So I am also a TPC member for many international conferences, and I conducted two conferences as convener. Okay, and I'm having around 18 years of teaching experience and 12 years of research experience. I am also heading a research group of computational intelligence in our university. So for past 2 years, I'm working in this quantum computing. So today I would like to give you a glimpse of what are the recent advancements that are happening and what are the challenges we have to face in quantum machine learning in the days coming by. Okay, so let me start our lecture with a small introduction. Like this could be the contents of the lecture for today. Like a small introduction I will give you, followed by a small explanation to what are the traditional machine learning algorithms are available, what are the differences between classical and quantum machine learning, some examples, and what are the softwares that are generally used now, and how many companies are working towards quantum computing, and some implementations we will be seeing with the help of PyTorch and IBM Qiskit and CARK. I will show you some small codes and small explanation I will give you to make you understand and feel like what is happening in at the present day scenario towards quantum machine learning. And I will show you some important stuff at the end, right? So if you can see, machine learning has been a very important technique and a very important tool for us for the past around 20 years. This this is the one which is helpful for many various disciplines around the world. So it's actually a subset of artificial intelligence, we say, and deep learning is called as a subset of machine learning, right? So machine learning mainly concentrates on feature extraction. We need to pre-process the data, and we need to actually configure proper features, and feature extraction need to be taken special care, right? So what is that making so special about machine learning is not a new thing for us, but what is the difference between machine learning and quantum machine learning is the one which, after deep learning got introduced, machine learning has some limitations. Like we need to spend a lot of time for feature extraction, but that automatic feature extraction is not there in machine learning. So to overcome that problem of feature extraction, we generally take into consideration the newly introduced deep learning for the past few years, which we're seeing. This is in classical computing or conventional computing, what we say, the role of machine learning and deep learning, right? So if your problem that you have taken does not require much about of designing own feature extraction models, then we generally go for opting for deep learning models. So hand in hand, machine learning has many advantages and limitations. The same way, deep learning also has many advantages as well as some limitations out there, right? But that is with respect to conventional computing or classical computing, what we have seen for the past 2-3 decades, right? But even though it's a very important engineering discipline, okay, and having vast number of applications in healthcare, especially where we generally depend upon early detection of pneumonia, early detection of cancer, or early prediction of COVID, okay, or early prediction of Alzheimer disease, Parkinson disease, or dementia. This early prediction, early diagnosis is very essential in healthcare sector. So due to this, generally classical computing takes a lot of time for performing this model execution and giving the expected output. So it takes a lot of time for us for processing our formula or processing our model and get the expected result, whether it will help for us or not. So due to this time lag that we are having, to avoid that particular time lag, we generally go for opting for quantum machine learning. That is, machine learning in quantum environment we try to apply. Why? Because quantum computing reduces this time lag. So within a less span of time, within very less time, we can perform the same task more faster and with the same accuracy or even better accuracy than what is performed at the classical level. Okay, so that is the reason in drug discovery also our quantum machine learning or quantum computing is gaining so much importance in US and UK at the present day scenario. And early detection of disaster management or air pollution, earthquakes, volcanoes, tsunami detection, many other cyclones, or which there are some causes that are covered by environment. Okay, so these things we need to manage and we need to predict early so that we can take the preventive measures and we can protect humanity from disasters. So in that also our quantum computing will play a vital role, and machine learning and data science will help us for that early prediction and detection. Okay, and there are also various applications in business also, like you sometimes expect inflation or recession happen, so you need to predict well ahead, okay, in designing our own strategies, and we have to protect business sectors also. Some applications are there where we have this quantum computing will be helpful for us, hand in hand with machine learning and data science algorithm. Learning, why it is a challenging task is why, because we have to define our feature extraction, we have to define our features, and we need to do a lot of pre-processing in machine learning. Whereas the same is not expected in deep learning. Okay, but the quantum deep learning is not that much advanced now. Still, it is in the early stage. That's why quantum deep learning I will not stress much on today. But quantum deep learning is also the near future coming by. The next 2023, there will be a lot of algorithms that will be floated in quantum machine learning and quantum deep learning. Already 81 companies are working on this particular quantum machine learning and deep learning. So speed and accuracy is the main important thing that we actually take for granted. So the speed and accuracy will be far better compared to that of classical computing. That is why we are going for opting for quantum computing in the present day scenario. See how it actually evolved. How it actually evolved. You can see in 1981, the first time theoretical predictions, theoretical principles were given by Paul. Okay, in 1981. Later in 1994, Shor's algorithm was discovered, and integer factorization, how we actually do it. Integer factorization using Shor's algorithm was introduced in 1994. Later, there were some more algorithms called Grover algorithm also was explained. In 1998, first working 2-qubit quantum computer was demonstrated, and in 2001, the first execution of Shor's algorithm was observed. So see, you can see it took 7 years for executing the theoretically explained Shor's algorithm. And in 2005, the first quantum byte was created by scientists at Innsbruck, Austria. And in 2017, IBM successfully tested was actually announced by Harvard. Okay, the 51 qubit quantum computer. Okay, so this is the evolution or timeline you can say for quantum computing. Okay, and if you can see, these are the traditional machine learning algorithms which we have been seeing for the past 2-3 decades. Same like we will be supervised learning, wherein again in supervised learning we saw classification and regression, and in unsupervised learning we call that one mainly as clustering models. So in classification, again we have support vector machines, discriminant analysis, naive-based classifier, nearest neighbor, and in regression we have linear regression, we have GLM, SVR, GPR, ensemble methods, decision trees, and neural networks. In an unsupervised learning, again, we have clustering. In clustering algorithms, we have our familiar k-means clustering and c-means clustering. Okay, you have fuzzy c-means clustering as well, and k-medoids we saw. Hierarchical and Gaussian mixture clustering algorithms are there, and neural networks we have seen a lot in unsupervised learning, and the famous hidden Markov model, which generally mainly used for speech processing, is also observed in classical machine learning in unsupervised learning or quantum computing, right? This generally why we use is expected actually to increase the speed and accuracy of computing tasks in any particular application. This is expected actually to enable different approaches to computational challenges in industries, like for example, healthcare, cybersecurity, and financial sector. Why? Because these three are the main important things for any country, for giving army or military or air force or no, any particular armed forces to protect our country. We require cybersecurity support for our nation. So, and healthcare is the most important, like you can say, place where a total world actually depends on. So that's where actually quantum computing plays a vital role, right? So these three are very important uh, areas. Generally, quantum computing is not technical verticals like artificial intelligence or virtual reality. Quantum computing also like seems a black box for most other the specialists working in the industry. That is, for others it will not be so understandable. It's not everyone's cup of coffee. People who are working day in day out in the industry, they will feel it better. They will understand it. But others, it will be like not so easy understandable. They find a lot of difficulties to understand the key concepts in quantum computing. Okay, so that's why a quantum computer what can do, it is not possible by classical computers, and there are at most 81 quantum companies are listed till date, and I will show you those companies also in the next few slides. Okay, and if you see what is actually that differentiates classical and quantum machine learning, you can see in classical machine learning we actually deal with classical data with bits, that is 0 or 1. Whereas in quantum, it's in quantum machine learning. If you can see, our classical machine learning actually consists of mathematical algorithms followed by CPU or GPU processing, and then we will identify pattern recognition. Okay, so the time lag, you can see huge time it takes actually. So whereas in quantum machine learning, you can see the time difference, you can see here. Whereas in time, you can see in quantum, it's like one fourth of the time or one third of the time that is taken. Okay, and the mathematical algorithms again, which are here, it is fed to quantum processing. Why? Because we have a quantum processing unit, QPU we call. Like in classical, we saw CPU and GPU, graphical processing unit. Here we generally call in quantum computing as QPU, quantum processing unit. Okay, and you can see mathematical algorithms, you can see, and how after superposition of states, how pattern recognition is observed. And the processing methods, you can see at the bottom left side, you can see the number 3 is the number of bits that are processed in classical machine learning, whereas here it is 2 power n, that is 8 possible states are possible in quantum machine learning. Okay, so this is the small diagram that shows for quantum machine learning, classical to quantum machine learning. How the transformation cyclic process takes place. What are the various important applications that you see in quantum machine learning? You can see like face recognition, entertainment services, self-driving automation, finance investment, recommender systems like in Amazon, generally Flipkart, Snapdeal, they use for recommender systems for recommending the products for the users. And genetics, this is the main field of research in healthcare. People are working animals to bring new revolutions and new research to happen. Okay, we are trying hard. Okay, to observe the changes in gene sequencing also, to observe like what could be the proper medicine that can be given for curing cancer. Okay, right, because correct medicine is not yet found, so they are working okay to work on particular quantum machine learning and data science algorithms. Okay, so this quantum computing in such drug discoveries, it will be very helpful. Why? Because in less span of time, it will generate the model and it will tell us whether the formula that we have given is correct or not. So that we, if anything wrong is there in the formula, we can again correct it and we can suggest another formula and we can again work the model another time. So in classical, to do a single task, if it takes in 10 days, the same thing of number of iterations can be performed in a single day, and we can expect good results in quantum machine learning. That is why the total world is looking for quantum machine learning in the coming days and the present day. Okay, if you can see, this is how quantum computing for advanced machine learning, how actually happens. You can see these are the like instance results taken from some particular assumptions given in various papers. Okay, so I've taken it from Google, where many good authors have given their own predictions related to quantum machine learning. You can see quantum clustering, quantum support vector machines, quantum principal component analysis, feature topology, and quantum deep learning they are proposed. And in case of quantum clustering, you can see that when data is represented in a very large dimension space, it becomes very difficult to perform clustering with a classic computer. So use of quantum computers is very good solution. Okay, so finding a hyperplane that separates many data points that are represented in a high dimensional space is so difficult on a classical computer. On a quantum computer, it can be solved extremely efficiently, as I said earlier also. And the goal of quantum principal component analysis algorithm is to find proper access along which to group this data. So it's something that takes order of n square on a classical computer, but in quantum version, you can do it exponentially faster. So whereas in feature topology, it's a method for finding the topological features of data. So this problem can be mapped to a problem of finding eigenvectors and eigenvalues of some huge high dimensional matrix. So in quantum deep learning is the future where you till date very less work is done, but we are expecting more work to be done in the upcoming days, especially in 2023. The exciting breakthroughs may soon bring real quantum neural networks, specifically deep learning neural networks, to reality. Many research papers have shown remarkable results in this area of research. So hope so our assumptions and our needs will get satisfied in 2023. Okay, you can see this is a simple example. I can show you like how some researchers have worked on this particular small case study. You can see in Google AI blog, it is represented. It's a quantum advantage you can see. So an experiment is done for DNA sequencing, where you can see the molecules, virus, and the physical world. Okay, or from any of these sources, the data is fetched through the sensors, and quantum information and classical information, how they are processed. You can see how the conventional algorithms, how they work, and how actually we learn for a physical state and how we learn for a physical process. You can see, you know, and how things varies in bits and qubits processing. You can see in the below diagram, you can see how classical processing takes place, how quantum processing takes place. It's a very good example to show like how actually quantum computing is processed. Okay, right. And this is another example you can see, which we can learn from experiments like how how in 1D dynamics and 2D dynamics or quantum learning does represented. Okay, and how it is represented in the help of Sakamo processor with the help of qubits. That is both system qubit and memory qubit. You can see in the diagram. Okay, and we generally apply unsupervised machine learning here. So a good An author represented this work in a good IEEE paper, you can see, and how this one works for 500 iterations and how this one works for 1000 iterations, you can see. So it's a good comparison you can see for 1D and 2D dynamics. Okay, right. So if you can see here, like what is the main difference between classical and quantum? So the first one you can see, right, in ML applications. So we deal with classical data with zeros and ones, and quantum data we deal with qubits. We deal with qubits, and you can see on-off state you'll see in classical, whereas here we see suspension of states in quantum computing, as well as logical gates are basic building blocks for classical data, and whereas quantum gates are basic building blocks for manipulating qubits. Sometimes we use some gates, what we call it as Hadamard gates, and this is how we represent Hadamard gate. You can see, okay, and logic gates are made using transistors, and quantum gates are represented by using unitary matrices. So a microprocessor is a package of several transistors linked between them to process the information. So the richness of the values of the qubit can be manifested only during the calculation. So you can see bits zeros and one, qubits zeros and one. And there are two possible exclusive states, whereas two simultaneous possible states will be performing in machine learning with respect to quantum machine learning. That is the advantage. You can process n dimensional, okay, states at the same time. That is the processing the states one after the other becomes difficult, which was observed in classical. Here, we process two states simultaneously, two tasks simultaneously, and we can get the output for the two tasks simultaneously. Okay, right? So in classical data, we see either 0 or 1, whereas in quantum, we see only 0. Initialization will be only 0. In classical, we have either 0 or 1, but in quantum, strictly, the initialization will be 0. And the representation, if you see, it is in the form of zeros or 1 in classical, whereas in quantum, we see vector of 2 dimension. Whereas in dimensionality, if you see, one binary digit in classical data and two floating numbers in quantum data. Okay, right. If you see the modifications, logic gates are used in classical data and quantum gates are used in quantum. So, and how you read actually these is 0 or 1 or deterministic values you see, whereas in quantum there is a probability that we will see 0 or 1 or probabilistic values you see. So if you can see, our machine learning has various applications, and we generally classify that in supervised, unsupervised learning, semi-supervised learning, and reinforcement learning. Where in supervised learning, again, we see classification and regression, where various examples like fraud detection, weather forecasting, image classification, diagnostic, estimation, expectation can be used. Whereas in unsupervised learning, we come across like clustering, dimensional reduction, where structure discovery, meaningful compression, big data visualization, such applications are performed. In semi-supervised learning, we see something called as clustering and classification. Okay, and the applications where we use in semi-supervised learning are for GPS data, structure identification, medical prediction, text classification, speech processing or speech analysis, and internet sequence classification. Whereas in reinforcement learning, we have classification and control, so skill acquisition, optimized marketing, bidding and advertising, real-time decisions are the applications which we are concentrating on. Okay, so these are the popular companies that we are seeing in quantum computing. These are the pioneers, we can say. These are the first few companies which have started working on quantum computing, and these are generating business at the highest level, and They are providing services also at the highest level. Where IBM is the first one which actually brought IBM quantum computer into reality. Nowadays, we are seeing AWS providing quantum bracket. Okay, we have Microsoft also. We have Azure Quantum. We have Alibaba Group working on that. We have Cold Quanta. We have AQT. We have Google AI. We have D-Wave, we have Atom Computing, Atos, okay, Dirac and Atlantic, HeroQ. We have various companies you can see. I would also like to show you some good number of companies hmm, that are given. Okay, so you can see here. Yeah, you can see here the blog that is provided by Quantum Insider, where 81 quantum companies are there in 2023 till date. Okay, right, and you can see these are the number of companies. You can see number of quantum organizations till date they are founded. So this coloring you can see these are nothing but the hardware components and quantum computers. How many number are there? This is in 2022. You can see. Okay, so if you can see who are the quantum computing giants, if you can see, IBM is the first one which was founded, and in 1911 this was founded actually. Okay, but IBM quantum computing came into reality in recent past times. Okay, in February 21, 2021, there are around 20 devices on the service. You can see. Okay, right, and so the IBM Quantum Lab is actually led by Vice President Jai Gambetta. He's an IBM fellow. After that, we have Google Quantum AI, Google AI, we say, and the third one we have Microsoft, and then we have Amazon AWS bracket. We have the fifth one we have Alibaba Group, and then Atos Quantum. Okay, right. We have Baidu, so it's from China, it's from Alibaba Group. Okay, this is another popular quantum computing platform. Okay, we have Intel, and then the second category they have classified is the top hardware focused quantum computing organizations. Alice and Bob is the first company. It's a startup actually, and the second one is Alpine Quantum Technologies. Okay, the third one is Anion Systems. It's it is headquarters is in Canada, and Atlantic Quantum is another important, uh, like a small startup, a company which is working good, very good recent times. Okay, and the venture span out of actually MIT, which in early stage tough tech companies, say Atomic Quantum Computing. Okay, so it's a Berkeley, California startup found in 2018 by Benjamin. Okay, and you have Bleximo is another quantum startup. It's building a full stack superconducting application, specific quantum computers, and these are used for designing many quantum algorithms and hardware to deliver first quantum advantage. So also we have C12 Quantum Electronics, Cold Quanta, okay, and D-Wave is the powerful company. You know, everyone knows D-Wave. It's a very powerful hardware manufacturing company in USA. It's a main company which also gives a lot of good support for high performance computers. Okay, so the world's best high performance computers are also processed through this D-Wave, they say. And this one also is helping Amazon AWS to provide services on remote mode. So very good company. We have also Dirac, HeroQ, and IQM. Okay, IonQ is the one which also a powerful company which is providing support for solving quantum complex problems, and this is also giving services to Amazon AWS for providing a lot of services. Okay, and the next one we have Nord Quantic, okay, and Orca Computing, Origin Quantum, we have Oxford Ionics, Oxford Quantum Circuits, we have Pascal, okay, and Photonic Inc. Okay, so we also have Planck QC, PSI Quantum is another important quantum computing simulator, QDOR. Your Kilimanjaro is another very important hardware and software team. It's focusing on quantum computing, especially with the help of Barcelona Supercomputer Center, University of Barcelona. Okay, Cura is another important company which is supported by MIT. Quandela is another one which was founded in 2017, along with Quantware and Quantum. Okay, and Quantum Brilliance is the another one, along with Quantum Circuits and Quantum Motion. So these are some of the popular companies, and still some more are there which are used exclusively, okay, for quantum computing, okay, in the present day scenario. Okay, right. Let us go back to our PPT again, and we'll continue with our lecture. Okay, so this is another important quantum machine learning model you can see using quantum transfer learning. Okay, a few authors have proposed this how to perform quantum transfer learning in quantum machine learning. Okay, with the help of PyTorch, Qiskit, and CAR. Okay, Penny Lane is another powerful company which provides these services. So how we can take a generic data set and some other specific our own data set for comparison, we take it and we pre-train this machine learning model using PyTorch. I'll give you some brief explanation with respect to PyTorch in the next slides. Okay, so this pre-trained machine learning model with the help of PyTorch, okay, so we perform the image classification and later we perform the transfer learning for this with the help of the hyperparameter tuning. Okay, this is then fed to the hybrid classical quantum machine learning. So, and we train it and test it at different levels with different data sets. And after the generic task are and specific tasks are released from these PyTorch based simulators, we then give that as an input to Qiskit in IBM Quantum Computer, IBM Qiskit, or to CARQ or QSKit using Penny Lane, the quantum computer simulators. In real quantum computer, we see with the Qiskit Terra, this is a real, actually, physical one, we can say, and this is the quantum computer simulators on virtual mode. We'll see where we actually work with IBM Qiskit along with CRQ and Penny Lane. Okay, so I can show you this simple example. Okay, this is a good paper actually. They have worked on this. So you can see this is the uh, actually blog with respect to quantum transfer learning. Andy Sharma is the person who actually has given this. So see, you can see he has worked very good in this particular project with the help of quantum machine learning using Python. Okay, he has given also the resources on GitHub so that you can practice them later. Okay, so how he has done, he has given a good explanation here. So using hybrid classical quantum machine learning, okay, and he has used x86 laptop plus quantum simulators on local classical computer, that is through Google CARQ and IBM Qiskit and Xanadu. Xanadu is another important company in that 81 listed companies, which is actually provided by Penny Lane quantum simulators. So x86 is the laptop with the Lenovo T480 series, an Intel-based i7 CPU and 16 GB RAM without GPU are used. And the OS is with this old project which was used with Windows 10 version with Anaconda. And the data sets that he has used for transfer learning, ResNet 18 model he has taken, okay, and which consists of 410 images he has taken, all classes he has applied through a random Google image search and downloaded images. Further, he has split into three subsets actually for training, validation, testing in this ratio. Actually, you can see 58% is used for training, 12% for validation, and 30% is used for testing. That is, 410 images is classified into 240, 50, and 120 respectively. So 240 images exclusively are used for training purpose. So how the experiment is performed, you can see and the results how they are obtained on ASMT 480 platform. Okay, so how epochs they are generated between the accuracy and the loss, the values also you can see here. Okay, so since this is transfer learning, we generally achieve quite a high accuracy in just a few epochs. So we only retrain the last layer with new additional data set on image actually. So classification actually shows how classical quantum machine learning through transfer learning is possible without achieving highest accuracy. Okay, you can see with the help of three backend quantum simulators like Google, IBM, Penny we actually perform this particular task using three different Google, IBM, and Penny how the accuracy so is calculated with different iterations. You can see this diagram. Okay, so the Penny Lane, Xanadu Plain Lane is the green one. You can see Google CARQ is the blue one, and IBM Qiskit is the orange one. Okay, and the training loss also is plotted, and the diagram corresponding to that is seen here. Okay, so similarly, these following illustrations you can see they are the training accuracies and validation accuracies which they are performed using IBM Q local simulator. Okay, so training or validation accuracy with respect to different iterations is seen here. Okay, and that you can see this is the training summary, and you can see here the training summary for training and validation loss. You can see here. Okay, so what is the values that you got it for error and accuracy? Also, you can see here for 120 tested images. Next is the quantum layer where 4 qubits quantum circuit executed at each job execution on quantum simulator. Okay, is shown actually. See, you can see on 4 qubits they have performed for 1024 shots. And the image classification output you can see here. This is how it looks like. This is the popular quantum circuit based output that you generally see on our simulator, on our IBM quantum simulator. Okay, so then you can build a hybrid classical quantum machine learning with the help of transfer learning for a pre-trained network. So what we generally do are we prepare the model, we retrain the model, and we predict what is the newly generated model. This is what actually we generally perform. Okay, so we have take the data set that is desired for us and perform this task and retrain it using hyperparameter training. Okay, and this is the code given. Okay, just excuse me. So you can see this is the code given. Very beautiful introduction code for us to practice. The author has given very nice use case for us for practicing quantum basics with respect to transfer learning using Hadamard gates. So he has defined very nicely, and the entanglement also is provided here. You know very well that quantum entanglement for a particular case only was received Nobel Prize in this year 2022. So he also uses different torch, that is PyTorch built-in functions also. So after replacing quantum layer, okay, he prepared the dressed quantum net with the help of the quantum circuits, and he reloaded it and tried it for getting the accuracy. The training accuracy he observed is 97%. Then again he retrained the quantum layer for finding out the better accuracy and predicted okay what could be the final output. You can see this is the final output he got it for wearing the mask or not the expected value. You can see it's the correct values and the wrong values that are given. This is the output that he got it using transfer learning. Okay, so always you cannot expect that predictions are not 100% accurate. Sometimes their mistakes do happen. So after that, so uh, he has given us quite number of good references for us, like quantum random number generator, how you can do, quantum teleportation, how we can do. Okay, so these are various examples he has given. Okay, in IBM 2020 B version, the IBM Quantum Experience, how we can process this further. It's a very good use case he has given for us for a better learning and understanding of quantum machine learning. So these are the latest advancements we can see in quantum machine learning and quantum transfer learning is a very good advancement, which actually showed the starting of quantum deep learning. Okay, because transfer learning we generally see in deep learning in machine learning, classical machine learning. The same quantum transfer learning also is realized in this present. The other important topic that we studied more or in classical computing is reinforcement learning, where Google and Facebook are working from past few years how to use reinforcement learning for their some of the projects, and they observed some drawbacks were observed in using TensorFlow and TensorFlow 2.0 or TensorFlow JavaScript, TensorFlow JS they called. They observed reinforcement learning was not uh, given complete results as the accuracy level expected in TensorFlow. They were not seen. So that's why they opted for applying PyTorch based reinforcement learning. And thanks to IBM and PyTorch, they brought in a good deep Q learning, DQN agent. Okay, so to work on this particular small use case that you can see in the diagram for OpenAI Gym. So we actually use this particular block diagram, uh, this particular example that I will explain you with the help of Google Colab. I will show you how they are actually doing this particular reinforcement learning using PyTorch, that is using quantum computing, using IBM Qiskit and IBM, how they're using PyTorch for their deep learning algorithms. So you can see they choose different random policy actions and sample environments, they record memory or updates and optimize these algorithms for giving soft target net update. Some wherever required, they use random number generators for replay memory, and the policy nets are proposed here, and optimization takes place with the target net, and it is reiterated and again until we get the desired accuracy and desired result out of reinforcement learning. So I will show you some important code related to this also. What are the key concepts that you have to learn to understand basics and advanced concepts in PyTorch so that you can apply this for quantum machine learning and quantum deep learning? You should have good sound knowledge related to tensors, data loaders, torch, transforms, and training the neural network. Good sound knowledge is required for that. Optimization studies, automatic differentials, using PyTorch, TensorBoard, and deep learning with PyTorch, we require visualizing models, data, training, and training with TensorBoard also is required. I will show you how exactly the TensorBoard looks like and how they are performing training with respect to TensorBoard. Also, I will show you there are a lot of tutorials available for us to learn on PyTorch with respect to this quantum machine learning. And also another important thing where a lot of research is happening in India and abroad is how to process image, video, audio, and text. Okay, so it's a speech processing and signal processing wherein quantum machine learning is becoming a real challenge in the present day. And as I told you earlier, reinforcement learning using PyTorch, the DQNM, we'll be seeing. Okay, and this PyTorch can be extended further, go more deeper into distributed environment. We see double backward with custom functions. We see fusing convolution and batch norm using custom functions. We see custom C++ and CUDA extensions, extending torch script with custom C++ operators, extending torch script with custom C++ classes, registering a dispatched operator in C++, and extending dispatcher for a new backend in C++. Okay, so this, if you can see IBM Qiskit specifications, if you can see how IBM Qiskit software is used. Okay, so the version that is used is Qiskit Terra. Okay, and Qiskit AR simulator is the version is 0.11.1. Qiskit Terra, the version is 0.22.3, and the Qiskit machine learning, see, the version is 0.510. Latest advanced simulator, if it is there also, you can use it. The Python version which was used for this particular example that I'm going to explain you is 3.8.14, and the Python compiler is GCC 9.4. The Python build, it was September 7, 2022, and the OS is Linux, which is used here, and two CPUs are used, and the memory that is required for it is 6.78 GB. Okay, so as I was telling you, like PyTorch is very important and powerful tool for our IBM QSuite. So IBM QSuite along with PyTorch, QGAN, Generated Adversarial Network, is an advanced topic in deep learning. But that advanced topic of generated adversarial network is already realized in quantum environment, which very few people know. Why? Because of lack of awareness in quantum computing. Okay, and QGAN is a very powerful hybrid quantum classical algorithm which is used actually for generative modeling tasks. And the algorithm uses interplay of a quantum generator, that is ansatz, and a classical discriminator, which is a neural network actually, to learn underlying probability distribution giving training data. Two things are mainly used here. One is generator and discriminator for optimization steps. And generator aims at generating samples that will be classified by discriminator as training data samples. That is, samples extracted from real training distribution. Discriminator is the one which tries to differentiate between original training data samples and data samples from the generator. That is, in other words, telling apart from real and generated distribution. So the final goal is for quantum generator to learn a representation for training data's underlying probability distribution. So the trained quantum generator, therefore, can thus be used actually to load a quantum state, which is an approximate model of the target. So this is the link, which is a very useful one, which is useful for us, from IBM QSuite, which helps us for learning IBM QSuite, in that how to learn PyTorch, QGAN, how to perform in quantum environment. I will show you that. Okay. So, and quantum computing also is performed with the help of Google CARQ. As earlier I told you that it is also listed in one of the powerful 81 quantum computers. So this is used for creating quantum circuits for NISQ quantum computers. So the NISQ is the very powerful organization which is helping for a lot of research for USA. Okay, so some examples for CRQ work results from these early adopters like Zapata Computing and QC, where quantum benchmark, Heisenberg quantum simulations, Cambridge quantum computing, NASA architecture, which actually gives an awareness for compiler based on temporal planning for QA/OA and simulator for quantum computers. And these are two another powerful links that will be very helpful for us for learning about Google AI blogs and quantum machine learning. And these are some of the references that I had given it for you. Okay, and I would like to show you one more important uh, link, which will actually give you a clear glimpse about performing quantum computing using IBM QSuite. Okay, so you have here, if you can see, this is an example I can show you. It's a good example. You can show you how you can see in Google Colab how you can execute quantum machine learning based upon PyTorch based tensor board. Okay, so what he actually is using here is using, initially he used our traditional matplot library as taken here. Okay, I'll zoom it a little bit for your purpose. Okay, so you can see he installed PyTorch, Torch Vision, Matplot library, and TensorBoard. Okay, he has installed this for applying quantum machine learning using PyTorch. Okay, so you can see using pip install Torch Vision, Matplot library, TensorBoard, we can download and install all the dependencies that are required for us. Okay, and a variant of Linet 5 against the fashion MNIS dataset is used. Okay, and you can see this is the PyTorch program that you can see for training the necessities. Okay, so you can see how we are importing PyTorch here, and we are also importing neural networks in PyTorch, and optimizers also we are importing in PyTorch here, and different image data sets and image manipulation are performed with the help of different transforms in Torch Vision. And you can see image display, where import matplot library is performed using PyPlot, and NumPy is used for any mathematics that you are going to perform here. And the PyTorch tensor board provides good support here for summary writers, okay, right, and which shows images in tensor board. So how we gather data sets and prepare them for consumption, you can see through this particular command, we actually collect them and normalize with respect to transform. So storing separate training and validation when fashion MNIST data set is performed here. So you can see this is the training that has been performed, and later the validation you can see, and then the data loader is used for training. Okay, then the validation loader is executed. So you also label them properly so that you will understand exactly the output what is generated with respect to the classes. And then we use Matplot library for us for displaying output, and formatted output is performed here. Simple if else structure is used here, and you can see after extracting a batch of 4 images, we can see we can create a grid for the images and show them using the Matplot library. You can see we have downloaded them and we have extracted them, and this is the output that you can generate. This is one example of using tensor board. Similarly, reinforcement learning, you can see similar. This is very important tutorial, must for the graduate students in India and abroad. They have to learn this for performing such type of operations in graduation is required, and they should learn how to apply reinforcement learning with respect to quantum and classical. Both you have to learn, especially in the present day. They should learn how to use this particular algorithm using PyTorch. You can see this tutorial will help you. So how we trained PyTorch based deep Q learning. You can see we performed this task on Cartpole version task. Okay, and you can see, okay, so he has taken this data set from the GIM website. Okay, so after taking this data set, he downloaded also the required packages. Okay, and see, you can see he has installed using pip3 installed GIM class control, and they have successfully installed them. And then they used 3 different things, very important things for PyTorch: neural networks, that is torch.nn, optimization using torch.optim, and automatic differentiation using torch.autograd. So you can see we are importing GIM, math, random, and NumPy, Matplot library. We are importing all these, and collections we have taken, imported different iter tools for performing our task. Okay, for enqueuing and dequeuing operation, for encoder and decoder autoencoder concept also we perform this. So similarly, we imported Torch for our PyTorch environment, and we are given some alias for performing easily in the program. So a simple if else will be useful for us for extracting the required information from the data set. And we use Matplot library here again for our displaying output. So if GPU is to be used, we can use CUDA processor here. Okay, right? So and we can replay this memory. Okay, so we generally will be using actually these for training our DQN algorithm. Okay, so what generally we see in DQN algorithm, 2 things mainly we see: transition and replay memory. Okay, you can see, right? So they defined how to perform this, and the DQN algorithm later is performed, okay, right, with the help of Matplot library and Huber laws. Huber laws actually acts like a mean square error, where error is small, but like mean absolute error, when error is large, this makes it more robust to outliers when estimates are very noisy. So we calculate this for a batch of transitions sampled from replay memory. Q network, you can see how we are performing this convolutional neural network on quantum platform for our uh, reinforcement learning algorithm. So you can see how we are generating this DQN, there is a deep quantum neural network, how this module is generated, and how we actually perform optimization. And we later train it using hyperparameters and utilities. Okay, you can see this is the hyperparameter tuning part, you can see we use Adam optimizers, okay, for performing this task, and different thresholds are taken here, okay, and how this is how we use PyTorch and Tensors for displaying the output here. Okay, so after training it with respect to the perfect optimized model, we can see we get using a CUDA processor, we get the output like this. This is the result which we got it. So another best example actually for reinforcement learning in using deep learning or quantum computing. Okay, right? So also you can see here uh, how the PyTorch QGAN uh, implemented here. Okay, right? So you have different tutorials here. So you can have the mathematics, total mathematics. You can learn here the random distribution, how random distributions are loaded, and what is the mathematics involved in GAN, how we actually apply that in quantum environment, what are the basics are there, how many probabilities are there, basis states are there. All mathematics is given here. We can understand. So very good references also are given here. So we can go through this tutorial. This is very useful tutorial. See, you can see how random number generators are processed here. Yes, here also he has seen, you can see he imported PyTorch here in IBM Qiskit environment, and he started executing this for some sample data for two-dimensional multivariate normal distribution. And here you can see how he's using Qiskit machine learning data sets for discretizing truncation. And okay, he's defining minimal and maximum values for training data. Okay, right? So, and he has done the pre-processing part here for the training data, and the discretization and truncation operation are applied here. And later you can see after applying these, a bell-shaped bivariate normal distribution is plotted with the help of these commands that are used in Matplot library. You can see this is the output, sample output that he has observed. Okay, for machine learning in quantum computing environment using QGAN. Okay, so we can proceed further still, and we can prove that the training was discretized using a histogram representation. So 8 discrete values are considered here, and you can see these are the outputs that he has got it using PyTorch modeling. Okay, and then uh, we actually apply uh, more of PyTorch modeling into this and convert data arrays into tensors and create a data loader from our training data using PyTorch. You can see this is a PyTorch data loader that you can see. And later we actually configure the required backend configurations for quantum instance, and AR simulator is used here. Okay, and the QA sampling is performed here with help of quantum instant for evaluation purpose, and we initialize the quantum neural network with the help of ANSATs here. Okay, and you can see this is how we actually perform quantum circuits. Okay, so uh, you can see how we draw a circuit and see what it looks like. Okay, so this is the output that you generally get it for a quantum computing environment. So this is the quantum circuit output that you got it actually. Okay, right. So using this command, we can draw this draw.mpl. You can see. Okay, right. So you can define the quantum generator later. Okay, and using our quantum neural network and torch connector, we can also define the discriminator, classical discriminator, and the loss functions are defined here. And what are the custom gradients that are required for our generator BCE loss function, and how we evaluate it in Qiskit environment. Uh, so is performed here with the help of PyTorch, and you can see this is the output that you can see for uh, PyTorch neural network. Okay, right? So we define the optimizers and visualize the training process. Okay, and after visualization across 2 iterations, we perform the loss and relative entropy, and the training is performed at the end using the evaluation of relative entropy, training discriminator, loss measures are measured, training generator is performed using the optimizer, and loss measures generator's ability to prepare good data samples are performed with this code. And finally, the generator loss that is observed at the back end, okay, so is also enumerated with the help of the optimizer that is okay. So this gives a good output for us to see the difference between loss and relative entropy with the help of iteration versus relative entropy and iteration versus loss. You can say this is the good result that we got it actually using IBM QScript. Okay, we can perform this in real time in IBM quantum computer, or we can also perform this in IBM quantum simulator, IBM QScript, and you can execute this code. If required, you can just ping me. I can share you the stuff. You can see this is the output for your cumulative distribution function. Okay, right? So these are some of the use cases and some of the examples, and I would like to share with you people. If you want to learn more of uh, quantum computing using IBM QScript, just type IBM QScript textbook in Google. You will get IBM QScript textbook. You can just open this particular textbook. You can open it, okay, and you can see, okay, you can browse all the content here, all required entangled states, quantum entanglement, Grover's algorithm, okay, so all algorithms, and quantum circuits, okay, quantum G and unsupervised learning, everything you can learn. You can start learning. Good documentation is given for our regular practice. You can see, you can also connect to the IBM quantum server and you can perform this task. You can see Grover's search algorithm is given, okay, right, and very good explanation and quiz all are given. You can learn Grover's algorithm and you can perform using also your uh, IBM quantum computer, okay, right. So it's a very good, what you can say, example. Okay, so you can see how it is generated and output you're getting. Okay, so these are the circuits that you get it for your Qiskit circular library. Okay, so you can perform all these your better learning. Okay, everything available online. Lot of information is available. It's all required is we need to sit patiently for a while with a proper internet connection and a good laptop, and you can achieve very good advancements. You can achieve very good advanced quantum learning in the near future. So all the best for your learning and all the best for your mm, quantum computing learning. So, and these are some of the references that I used. I thank the authors, all the authors listed here in my PPTs. So, and all the authors who have given very good literature online. I acknowledge their support in for Google. So they provided a lot of resources online for us for learning, especially the PyTorch community for the PyTorch tutorial, TensorFlow community for the TensorFlow tutorial, and the IBM for IBM QScript learning environment provided online for learning. I thank one and all for providing this resources for making this lecture. So thank you for IEEE Turkey division for giving me this opportunity to share my views towards you, for all the young professionals connected here, for all the IEEE members connected here. Any queries from the audience, anything you have? Uh, so I'm ready to help you out. If you have anything would like to share with me, you can also write to me at, this is my email ID and mobile number given. You can always reach to me. Okay, I will be readily to help you at most what I can do for you people with respect to the recent advancements and challenges in quantum machine learning and quantum deep learning. There is a huge way to go abroad. Lot of road is there ahead. Hope all things will go. Thank you all. All the best. So, any questions are there? Let me check.
There's a question in the screen. Can you see?
It is not an easier task wherein quantum computers can become personal. Why? Because quantum computing is very expensive. Okay, even big universities also cannot afford to purchase quantum computers and make it personal. Okay, it what you can do is only you can take a remote mode licensing only can takes place. It's not so easy to exhibit like quantum computing coming into reality in our laptops. So it, it takes few more years actually for actually to bring that particular thing into reality. It's an expensive thing, and hope for like D-Wave, like companies, they manufacture and they bring into that quantum computing into reality, like our how we are using advanced laptops now. More advanced laptops which are quantum computing based will come into it. It takes few years, not so easy, but it takes few years. All that you can do now is you can connect on remote mode and you can access using Amazon AWS bracket or IBM. We have IBM Qiskit, or you have Microsoft Azure. You have quantum. Any other questions? Yeah, sure. You send me a mail. I can send you the tutorial link. I can share you. You can drop me a mail or send me a message uh, to this number. I will help you out. I'm ready to help you on this mobile number. You can send it, or you can mail me. I can help you with the tutorial, or if you require some more important information from PPT, you can note down my mobile number or email ID. Okay. Next, anything else are there? Any other questions? So, can we close it? Can we stop live and can we close the session? That's all for today.